Right, we're all set up. The next talk will be given by Luis Marcassa from Brazil.
Well, thank you. I want to say thank the organizers for putting such a nice meeting together and inviting me over. And I want to talk about excitation of rubidium Rydberg atoms inside of a microwave cavity. Well, last week I was about to pack, and I thought, well, London is going to be hot. It's summer. And then I had this subtle surprise, that in fact my winter, it's hotter than the wicked summer here in London, so I have to repack. In fact, I brought my more winter clothes, than I was planning to. Anyway, I also want to remind people, I don't know, Jim, we were in the CATMIN in Paris. Then we were in CATMIN in Waterloo last year, and Rosario, I didn't forget you. Okay, so have to be for the next. So in 2 years, we know where we're gonna be. Well, I'm gonna give you. Well, Rosario asked me on Monday what I was going to talk about. And I told her that I was going to talk about something that I did not understand by that time. Luckily, since then, I got talking to Hossein and talked to Jim, I learned more. And now I have a better feeling what's going on here in our experiment. Anyway, so I'm going to give you an introduction, experimental setup, results, and some perspective what we're going to do in the next months. So, well, Rydberg atoms are extremely sensitive to black-body radiation, everybody knows. And the effective lifetime depends on the black-body radiation. And in fact, in my early days, when I was very young, when I started to do Rydberg atoms, the first thing I did was to measure lifetime, And this is a paper that I published. It was basically a review of every work that we have been doing in lifetimes, but other groups also have contributed to measuring lifetimes with different techniques, with more precise measurements. But in general, black-body radiation model can explain quite well the measurements. So a few years ago, I had a new postdoc, had to learn about how to do measurements in lifetimes, and about how to work with Rydberg atoms. And I told her, well, let's do the following. Let's do one thing that I know how to do. That's measure lifetimes. So you can measure lifetimes. You're going to go know the feeling about exciting and detect them and so on, and make sure that you understand what's going on. And when she did, it turns out these points, which does not agree at all with theory, So this is the theories, two different theories for 0 Kelvin and the 2 different theories for 300 Kelvin. And it did not agree at all. It was really far away. So by talking in one of those meetings in Recife, I think was Robert, proposed that, well, maybe, the cavity that you have, it can be seen as a lossy microwave cavity, which can change the distribution of the black-body radiation. So we went back with a model considering that, yes, well, before the measurements that we did in the past, we made it in a large vacuum chamber, And it was a small vacuum, a small metal vacuum. So we did this, made a model as a lossy cavity, and we were able to represent it. So I was all happy and said, well, now we should probably put that inside of a microwave cavity and see what's going on. Now, similar results have also been seen by the group in Pisa. They have a different setup. They have a glass cell that they can modify, putting meshes and so on. But they see similar results. And that's not new, because if you look at Henry Hewlett's thesis, PhD thesis, he has used this changing of the black-body radiation with plates, and he measured different lifetimes, so that this is not new. So the goal here was, well, let's take a microwave cavity, make a mock inside, and see what happens. Well, I don't have much of the money, so I cannot say, well, let's get a bright new microwave. So I went to a colleague. He does work with clocks, cesium clocks, And he had one setup that a student, a master student did that was try to use a mott as a clock. So we took the chamber. The chamber was designed for cesium, so it has a resonance in 9.2 gigahertz. So we just made a standard mott, nothing special. So just is this kind of setup that is a cylindrical cavity inside. So we made a mott there. And of course, we have to realize which are the modes that we can excite in that cavity. So, well, it is important, since I was interested to do dipole transitions, it's important that I have a no zero electric field in the center, So we decided to go for the TM modes, the transversal magnetical. So it guarantees that we have some of those modes will have a no zero at the center. And in fact, what we did, we have measured a bunch, since that was not designed for that, we had to measure where the states we had resonance in this cavity. And we measure all this cavity. Some have better resonance than others. And this one, the Q is about 1300. So we decide, well, let's see, those are the resonances we have. Now we have to see if that matches any atomic level. So we have to see if we can go to from once, basically in the setup that we have, we can excite either S or D, So we can either, so if we have to consider the starting states, either S or D, and we have to see if when we can make a transition either upwards or downwards, And by sorting all the states we had, we discovered that we had the two matching states. The one that can go up, that's the 59D, and the other that can go down, that's 67S. Well, we can go to, if we go to lower frequencies, there are more states available, but it means higher quantum number, and I didn't want to go there. I want to go to lower numbers, So, and if our colleague also made so we decided to take that 13 gigahertz mode, And our colleague made a calculation how the field should look like. We know the field should vary about 1% at the center of the mott, So that's basically what we had inside of that game. So how can we do that? Well, we can, let's keep things simple. Let's start from a mott, excited with a blue photon, and just put this 1305 gigahertz to excite it down to the 66p, So we will go to the 67s and go down. So once you are doing this, what we are doing basically, we are introducing losses in the experiment. And you can measure them. Of course, depending on the velocity that your scan velocity of the laser, that will produce distortions in the spectrum. But at the beginning, I'm not concerned about those distortions, Once we have defined where are the lines that we really want to measure, we can do a pulse experiment that we can measure the states before we excited and after we have excited, or something that may vary from 5 to 50 milliseconds. And then we'll do some averaging, just to guarantee the quality of the data. So that's the kind of spectrum that we get, So this is 67S. It goes to the 66p, and what we see, well, these blue lines here are the hyperfine states of the 5p, So you may have a different excitation. And these states are just because of the scan that we are doing, I will show better data after we are there. So but you can map and you can see, well, there are weird stuff on the blue, there are weird stuff on the red, So let's change to another frequency, another frequency that's also resonance with the cavity, but you see that now the spectrum changes completely. Although all the part on the red, on the blue, on the red side is gone, So let's change now the state. So if I go to the 66S, but still keep the frequency at the microwave cavity, then I start to see stuff on the red. So I see these states on the red, and I see that the 66 as state bends upwards. No. When I got here, I had no idea why it's bending, but now I know how to explain you why it's bending this way. If I go to 6/8s, still keeping the frequency, the microwave cavity, you can see that now the state bends down, and we have a stop on the blue side, you know. And basically, this I did not show you the details, but those are the blue. Those results are the frequency of the blue laser scanning as a function of the microwave power. You know, so this is a plot that one of my coworkers like to do, is all in colors. You know, so you have the frequency of the blue laser here, and you have the microwave power. You know, so we have this kind of stuff. We were puzzled by those results, so we decided to go and do something a little bit. We said, well, let's go to a different state. I told you, I showed you the data for the 67S, which is resonance with the cavity. Let's go to the 59B state that also is resonance, but now with a different frequency from the cavity. And what we see now, we see a peak that's on the red, on the blue side of the spectrum, you know. And then, of course, it's different. It has less structure than the. So let's change the state. Now I keep this. I go to another state. I go to the 65B, and I see that, you know. So I was puzzled. We were puzzled by that. But anyways, those spectrums were not very good because, as I point out to you, it has this effect of the scanning of the velocity scanning of the blue laser. So it has this state, you know. So what we did, we took the blue laser locked to a cavity. Thanks, Mark, for helping us up with the cavity. You know, so we locked the laser with the cavity, and we scan. Now we can scan the laser, scanning the frequency of the cavity. We can scan the laser more precise, and we can do also a pulse experiment. You know, so we don't have the light all the time. You know, and what we see, if we go back to the 67, now we see that same kind of data, but now with much more precision, without this distortion of the scanning. So we see we are able to see even small, quite small losses in the spectrum. You know, but we see all those things, and they kind of. And this large one, you know, this large one is just the atomic that you would expect. You know, it's just exciting the atomic state. And of course, if you measure this, it's just an outer tone, and you can have an idea the power that you have inside. You know, so my colleague, we measure. Well, you know, it's very tedious. It takes very long to do this experiment. So a whole scan like this can take several hours. So to avoid the scanning where there is nothing, we decided that, well, we are going to scan only where we really see something, you know. So we took the measurements for each of those peaks in small frequency intervals, and we vary the RF, the microwave intensity, you know. And we get still the same kind of plot, but now with a much more detail here without this scanning architect, you know. And by measuring this splitting on the 67B, we know that we have a field about 30 millivolts per centimeter at the maximum. We did again for the 66. And we did it for the 68, and again we see on the 66 we see this stuff on these peaks on the red, and you can see that some of the losses are higher, 60 or 70, you know. And on the 68 we have stuff on the blue side, you know. So we did also for the 79B, and we see a little peak, and it's in agreement whatever we had before in this CW mode, in the CW operation. So we may ask ourselves what's going on, and you can ask, well, we are in a cavity, and what we have, well, you may ask, is this two Rydberg interactions? It's one Rydberg interaction. It's multi-photon, microwave photon. I don't know. That's measured. So we see one of those peaks. We just took several scans in one of those peaks, and we clearly see that as a function of the blue laser, it's linear. And of course, it can go up in a regime where we believe that there is blockade and the density is consistent with blockade. So we know that it involves one blue photon, so it should be one Rydberg atom. And if we measure the microwave intensity dependence, we also see a linear dependence. So we believe this whole process has to do with one Rydberg photon and one microwave photon. So how do we explain that? Well, that's what I learned this week. Well, one possible explanation is the following. At least well, I know how to explain this data for 66 and 68. Well, when I have 68, 66, the separation between the 66 and the 65 is larger than the microwave cavity. So the microwave photon is going to be here. So when you scan this blue photon, you're going to be connecting below the 65. That's why we have those red lines. And when we go to the 68, then the splitting between the 68 and 67 P is less than the microwave photon. That's why you have to go to the blue, And also it makes sense why it bends, this bends upwards and this bends downwards, because if you imagine that this state goes up here and it's a resting state, and then the same stuff happens here, So, but you may ask yourself, well, there is more stuff than only this atomic picture of resting states. And to be honest, I believe this has to do with molecular potentials, but that still needs to be verified. But this explanation also holds for the other states we have measured. So just to tease you, as you can see here, we start with our measuring the potential, and suddenly you can see something that looks like a phase transition, My colleague George believes that it is a phase transition. So he's there, well, he's watching us, but he's trying to measure this. And maybe a bistability, I don't know yet. It remains to be more, we need more data, So perspectives, well, I believe in those molecular states, you still have to do stuff. So maybe they are dressed molecular states. Maybe that also will explain why that high losses. And we have to do, of course, more phase transition and see if those stabilities are right or not. And we have to measure lifetimes. I have to thank you. I thank the support from the U.S. Army, the São Paulo State Foundation. And this small logo is the amount of money the federal Brazilian government gives me. So that's and I have to thank my co-workers, George and Daniel, that are in my institution right now. And the good part of being supported by the U.S. Army is that we get invited to the 4th of July party at the consulate. I met the ambassador, the consul, and took a picture with everybody. Thank you for your attention.
Questions? So maybe let me start with one. So as you have this microwave dressing, you would expect like you're inducing a dipole moment. So would you expect that as you crank up your probe power that you see like some stronger effective interactions then?
I hope so. It has to be still to be understood and to do more experiments for sure. Yeah.
Going back to your early experiment where you just had a simple can or a vacuum chamber, you would also expect to have Q-dependent frequency, or the Q factor depends on the frequency. And can you go back and see whether you would have seen such thing?
I know, not now, but I may do. I don't know. We are discussing if we go back to like doing a vapor cell and try to measure in a vapor cell. I throw that can long away.
Because with this vacuum chamber, you immediately get Q factor of 10 or maybe 20 without doing anything.
Yeah, that's true. But I don't have that anymore.
a couple of days ago, we heard the talk by Hannes Sayer, like who also talked about black body radiation, and he saw like some effects of collective or like effects that depended on the geometry of how you place the atoms. We also see.
Oh, no. Right now it's just a lot. You know, there is no.
But you can explain everything in a like kind of a single particle model. There are no, you know.
Well, so far it seems to be single particle model, but I guess we have to have more data. You know.
Yeah. One last question.
So you measure the lifetimes of your currents?
Not yet. Not yet. Is the next set is the next step. Yeah.
Temperature.
Oh, the temperature is a standard mod, you know, so it must be like 200 microkelvin, nothing special. But the chamber is at a 300 Kelvin.
All right, with this, let's thank the speakers again.